My name is Ashish Mahabal and we'll be continuing with the best programming practices module. So one thing that we'd see this time is what it is that one should do before the project starts. Of course, during the project you'll be doing lots and lots of things, but equally important are various things that you must do before the project starts, and that includes digging for requirements. Be thorough about trying to find out what it is that will be required in the project. Then document those requirements as much as possible. Make a use case diagram. Who is it who will be using that project? Who will be running it? And what are the conditions in which the project will be run, in which the program will be run? Because once you know that, once you have those diagrams, then it will give you a better idea as to how to go about making that a particular program or project. Similarly, maintain a glossary. Many times people who write the programs do not have enough domain knowledge for the domain in which the programs are being written. So it is very important to get to know which are the terms in the domain that you'll be needing, which are the computing terms you'll be needing, and once you have a glossary of that, how they're connected, how they work with each other, that is important to know. Similarly, I cannot overemphasize the importance of documentation. Do as much documentation as possible at every stage. This not only includes comments that go into the programs, but also meta comments that can go into configuration files and external README files, etc. So document as much as possible. One trade-off one has between maintenance and development is that clearly if you do very quick development, or if the development seems easy, very likely the program will not be maintainable. Maybe some shortcuts have been used, etc. So be thorough in your development process. As a result of that, you will find that the maintenance becomes that much easier. You yourself will very likely be maintaining the programs, or one of your teammates will be. But in either case, if you want to save everyone some grief, then maybe the development process should be thorough, deliberate, and in appropriate short steps, because the projects live much more longer than one expects them initially. And for that, what you may have to do is to adopt a more complex language. By complex language, I do not mean complicated language, but simply complex enough that incorporates all the structure that is needed in the specific project. And that will automatically make it readable. It will show the relationships between different parts of the program, and you'll be better off. So again, what should be involved when you start a project and take various steps in order to complete it is check the requirements of the specific module, specific part that you are working on. Go ahead, do a design related to that, implement that design, and then integrate that design into what has existed until then. And of course, one critical step at that point is validation. You should validate the work that has been done. This also applies to when you take libraries or programs written by others. So when you are basing your work on that already done by others, you should validate various items within that. For instance, even things like numbers and characters. What is being called a number? Is it really a number? What happens if you give a character as input? Or vice versa, if something that's being called a character, what happens if you give a number as an input? Similarly, make sure that all the constraints are correctly met. Here you see a diagram of the sky where a particular parameter called declination goes from -90 to 90. And if it appears in one of your programs and someone gives as input number 100, what is it that's going to happen? Then check consistency. Are you saying contradictory things about the same point at different places in the program? If that is so, then better you have to resolve that. So whenever you take someone else's programs, make sure you do that. But then you should not trust yourself either. All those above things you should do to your own program. Whenever you have written a piece of code, make sure you validate that with consistency and for constraints as well. But despite all this, what is going to happen is that there will be cases when things will go wrong. Some parameters will not be correctly input. And on such occasion, what you should make sure is that your programs crash early rather than late. For instance, if a particular subroutine needs 4 arguments, and you go through a lot of computation and then try to validate whether the 4th argument was in the correct form, and you find that actually you did not like a negative number to be there, then crashing at that point is not a good idea, because already you have spent some time doing computation that involves effort on the part of either computer or time spent during the computation. So it may have been much better if you have looked for all the arguments that are being given, whether all of them are consistent and they follow the constraints that you wanted them to be. Then if you have to crash, if you have to come out of the program, you better should do it in a way that does really crash rather than trash. By trash, what I mean here is leaving a lot of messages which either do not make sense or do not provide important or useful information to the person who's trying to run the program. So Perl has different ways of coming out of a program. If the die command is used, the program simply dies. It doesn't do anything else, just comes out and doesn't tell you anything that is reasonably important or useful. But instead of that, you could use also croak, which then blames the caller. It tells you which subroutine called that particular line which caused the problem to stop and the program to stop. Or you could use something like confess, which gives even more details. It can go into a fairly long trace telling you this routine was called here, that routine was called there, and where is it that the problem really originated. So related to that is try and catch, where you can say that the program should attempt to do something, and if it fails to do that, then what are the possibilities that it could, possible steps that it could be taking. And that is where exceptions can be raised. If an exception has to be raised, you have to ask, why did that situation come about? Was it a valid input or not? And then whether you knew such a situation will arise, and then take appropriate cases. So let's see a specific example of the try except. Here you see in the screen two parts. The top part is one way you should be using try except, and the second part is where it's too broad, so you should not be using try except there. So in the top part you see that we are using a dictionary in Python called collection. It has various keys, and we are saying that take a particular key and find out what its value is. And we are asking the program to try getting the value of that key from the dictionary. And then we say that if it doesn't find that, then it should return a function called key not found with that key as an argument. And if it is successful in getting the value, it should simply handle that value using another function called handle value. So this will go through quite fine. If it doesn't find the key, it will tell you that the key was not found. If it was found, then it will do an appropriate thing with the value. But on the other hand, you can try to make the try except too broad, as is shown in the second case, where you are combining the top two things by saying return handle value of the value that is returned by the collection for that particular key. Clearly, if it works, and you get the correct answer. But if it does not work, then your exception says a key not found here. Well, that may be part of the problem, but it is also possible that the key itself was found and the error was in the handle value function, and that is not clear at all from the exception that is being indicated here. So you have to be careful that you do not have too broad a case of try except. Then further about finding or eliminating bugs and so on, you should try not to optimize the code, but try to benchmark it. That is, try to find out where more time is being spent, what is a better way of using a particular structure. With optimizing structure, you can measure them rather than optimizing them, where you find out what is the size of each element of the structure, and if you're going to have a very big list involving that structure, how many bytes it's going to take, and if that is the appropriate form. Then an important thing to do is to cache data when you can. And this is very important, especially when one uses either recursive functions or lists which involve a large number of computations, and possibly some of the computations are going to be called in again and again, either within the same computation or by different users in the same program. So we'll see an example of that next. The other thing to do is also benchmarking the various strategies for caching, because even for caching there can be various algorithms, and for your particular situation one algorithm may be better than another one. So it's a good idea to look at different ones there. The same thing about optimization goes for applications. You don't have to try to optimize an entire application, but you should profile it. That is, see which part of the program takes up most of the time, takes up most of the resources, and try to reduce that. That way, you'll be comparing apples to apples rather than trying to say that, oh, the length of this subroutine looks longer, and that is why maybe I should try to reduce that in number of lines rather than the time that is being spent in that particular one. So here is the example of memoization. It's a simple program in some simple subroutine of factorial, and a factorial of a positive integer is, of course, multiplication of that number with all smaller positive integers. So Factorial of 4, as you know, is 4 times 3 times 2 times 1, which is 24, or factorial of 5 is 5 times the factorial of 4, 120. So here what's being done is that we start with an empty dictionary called factorial memo. It doesn't have anything to start with. And then when the first factorial call comes, as is shown in the last line of this program, called factorial 10, it'll find that factorial 10 is missing in the dictionary. So it'll try to calculate factorial 10, for which it needs to calculate factorial 9, and then factorial 8, and factorial 7, and so on. But the moment any of those is now calculated, that gets put in that particular dictionary. So whenever that call comes again, you'll already have an automatic answer, and you can just return that. And so after factorial 10 has been calculated once, if you call factorial 5, the answer will be ready. If you call factorial 7, the answer will be ready. Only if you call factorial with a higher number, say factorial 13, it won't be ready, but it can then get factorial 13 equal to 13 times 12 times 11 times factorial 10, which already you have, and then you'll have all numbers, all factorials up to 13 in your program. So this is how you'd go ahead and do the memoization, and will help you caching your earlier results. Similarly, here is how profiling can be used. The Python module called C profile can be used, and here we are seeing how the C profile will work with a particular regular expression of compiling hello world. And just that single call through C profile indicates that there are 238 function calls, including 233 primitive calls. And of course, this is a single statement, so it practically runs in 0 seconds, and all the different calls here show that they ran in 0 seconds. But for a real example, what would happen is that it will show you which of the internal statement, either primitive or one of your function calls, is taking more time. And then that is where you can try to reduce the amount of time. So in general, you should try to benchmark things, and there are utilities available for that. The benchmarking game allows you to compare different installations, different programming languages overall. But if you go to a specific programming language like Python, you have routines, you have websites, entire websites available to just compare various modules within Python too. So you should definitely take a look at that. Then let's look at some different aspects of programming. What are the necessary ingredients of a good program? The program should be robust, it should be efficient, and it should be maintainable. So what does one mean by a program being robust? That it should be able to handle different cases easily, like edge cases in particular. Those can be the most troublesome ones. Is the first case handled correctly? Does the list start with 0 or 1, and whether that has been handled correctly? Or is the last case that can come about handled correctly? Similarly, whether there are appropriate tests for different kinds of errors. How is the error handling itself done? Are exceptions raised correctly? So if you build in all these things properly, then you're going to have a fairly robust program. And one can check for overloaded cases in this fashion. Here what we have is a function simply called square, and it has a single statement which returns x times x, where x is the input. But then we run something called a doc test within the comments that are given up there. So we have various examples. It can take 2 as input, and then it should return 4, and you have -2 as input, and it should return 4. You can even input a complex number and get an appropriate response from that. So you should be making sure that if you have overloaded cases, they are correctly tested, and they in fact give what you want to come out of them. Similarly, with efficiency, of course, a chain, as we all know, is weakest when you find the weak point in that. So you should try to ensure that you are working with strengths of whatever language you are using, whatever module you are using, or whatever combination of those you may be using, and that you should avoid weaknesses. A specific example can be especially with compatibility, where Python 2.7 and Python 3, many people have not made a switch from Python 2.7 to Python 3 because something as fundamental as the print statement has changed, and obviously people don't want to go back and change all their print statements. So this was a case where backward compatibility has not been built in for whatever reasons, but one has to be aware of that, and when one is writing programs, one has to make sure that the trade-offs are taken into consideration correctly. Then coming to maintainability, you should remember that more time will be spent in maintaining codes than it took to writing them, and that can be a painful thing if the code is not well written or if it is not maintainable. Because when time goes by, you don't understand your own code. Forget about the code that others have written. So make sure that you have amply commented the code. Then in most cases, you yourself may maintain it. So help yourself by making your code maintainable right from the word go. And that can be helped by using consistent practices, as we talked earlier a little bit about braces and brackets and spaces and line lengths and tabs and blank lines and all of those. So make sure that you have consistent practices. If you are managing a big team, make sure that they follow consistent practices as well. Next time, we'll be looking at design by contract and about comments and arguments and some related aspects.